Alright, this is 9.2 Waves at Media Boundaries, and I think this is an exciting lesson because it's really when we start to talk about some ideas behind music and behind what we call standing waves, which are a really important idea. So we looked at standing waves. When we looked at these in class, you might remember just yesterday, in fact, we looked at standing waves with the slinky, and we saw that if I waved the slinky back and forth at the right speeds, it created these little patterns that looked like the wave was just moving up and down, and it wasn't moving left and right along the slinky at all. That's what it looked like. So if you look at the picture to the side here, we have a wave that goes down, up, down like this, and it's just sort of bouncing back and forth between its maximum points. And that's what these standing waves look like. So a standing wave is a wave that looks like it's standing still. So it's at a sort of constant position on the string, and it's just going up and down. Now that's not actually what's happening. There's actually some funny stuff going on where the waves are bouncing left and right along the string, and there's a whole bunch of waves, and they're all interfering with each other, and they cause this end result. So that's the cause here. We can say that waves interfere with their own reflections as they bounce up and down the medium. Okay, so that's the cause of these standing waves. The waves actually are traveling left and right along the string, and it just ends up looking like they're not. Okay, on these standing waves, we have a few special points called nodes, and nodes are these points here where the string or the medium is not bouncing up and down at all. It looks like it's just staying still. They stay at the equilibrium, at the 0 point. So the nodes are points where the particles aren't moving. And antinodes are the opposite. They're these sort of maximum points or the minimum points. And this is where the string is really bouncing up and down the most. These are the maximum points. So they're points where the particles move the most. And I'll put in brackets here up and down. Now, I mean, it's up and down in our picture. There could be other situations where it's, instead of up and down, there's pressure waves. There's all sorts of different types of standing waves. But for our picture on the right here, that's where it's moving up and down the most. Okay, so we're going to look at 3 different types of standing waves. And we're just going to learn how each of those works. So our first here is when we have 2 fixed ends. And what I mean by a fixed end is that the end of the medium is held tight in place. So that it must have a node. Remember, a node is a point where it doesn't move at all. So if you look at the pictures below, you can see that the ends of the medium, let's imagine this is a string, and a string, let's say it's attached to 2 fixed points. Maybe it's attached to the wall. here, and here. And if they're held in place there, that means that the string needs to stay there, and the only place it can fluctuate is in between. So it needs to have a node at either end. So this is what we mean by having two fixed ends. So when it has two fixed ends, we also call this, it's also called fixed, 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 and we see these the most in string instruments. So let's take a look at what this means here. If I'm forcing both ends of my string to have nodes at either end, I'm holding this end, somebody else is holding this end so it doesn't move, but I'm making it sort of vibrate up and down in this sort of standing wave pattern, well, the first option I have is where it just vibrates up and down this way, where there's one antinode and that's it. And you see this antinode, it's going to vibrate from a maximum down to the minimum and back and forth like this. So that's our option, and you might remember that, again, I demonstrated that when we looked at it the other day. And I was waving it back and forth fairly slowly to get that, that sort of shape. Now we call this, when there's just one antinode and two nodes, we call that the first harmonic. Okay? We have a few different ways of writing this here. You can see that on the left here, we call that F naught, F0, so that's the fundamental frequency is what we call that, so the frequency 0. You can see that the number of nodes between the two ends is 0. You can see that we call that the first harmonic, and we also call that the fundamental frequency. Okay, so there's a whole bunch of different names for this exact same thing. And the last thing we can say is, so we're calling this the first harmonic, so you can see n is equal to 1. And we have an equation for the length over here, and we're not going to get into that equation quite yet. We'll talk about that below. But you can see that as we add more nodes here, now we have F1 has one node in between. You can see we still have the nodes. We're holding it still on either end. And in the middle, we also have a node. Right, and so then our string looks like it's vibrating up and down here, and up and down here. But there's a point here where it's fixed, and it's not moving back and forth. So at a certain point in time, our string might look like this. And then it might change so that it's looking like that, and it sort of goes between those two positions. That's what our second harmonic looks like. So this has one node in between the ends. We call that the second harmonic. We also call it the first overtone. I want you to sort of ignore this column here because it maybe is making things more complicated than it needs to be. Notice that from second down to first, it's confusing, right? So that's okay. You can ignore that final column. The important thing is we call them the first harmonic, second harmonic like this. And you can see that each time we add a node, the shape changes. So now we have two nodes in between, and this might look like this to start with. And of course then each of these antinodes is going to vibrate up and down like this. That's what we're talking about here with our standing waves. Okay? We call that the third harmonic. And the fourth harmonic, that's just when we have 3. So notice that if I call it the fourth harmonic, then there's going to be, so if I say n is equal to 4, I'm calling it the fourth harmonic, and that means that there's going to be n minus 1 nodes between the ends. Because we have 1, 2, 3 nodes between the ends. Or we can say there's n plus 1 nodes total because we have the nodes on the ends. The shape of this guy looks something like that. And again, this is going to vibrate up and down. Okay, so hopefully that makes sense. If it doesn't, please talk to me because this is an important idea and I really want you to all feel like you understand what's going on. So that's a string. And the next category, the next thing that we have, that was two fixed ends. Now we're going to look at two free ends. So a free end is where the end of the medium, can move freely. So it will have an antinode at that point. So we're saying that at the end of this medium, if it's a free end, nobody's holding it. It's not attached to anything. If you imagine a string, that string is allowed to wave back and forth as much as it wants. So that is a free end, and it's going to have an antinode there because it's allowed to wave back and forth as much as it possibly wants. So that it's going to have an antinode, which remember that means that it has a maximum or a minimum value there. If we have two free ends, well, we call this is also called free, and we see this the most in brass instruments. Oops, brass instruments like that. I won't get into the details of why those are in brass instruments, but if you want, we might actually talk about that a bit in class. I'll bring in my instrument. We can take a look at what that's doing. Okay, so we have our two free ends. Here's a picture of what that looks like. So usually when we're talking about free ends, that often has more to do with air. So you can imagine here this picture. Let's imagine this is a tube, and maybe I've taken my trumpet and just stretched it out so it's not shaped like a trumpet anymore. It's just a long tube. But you can see that if I'm talking about my air pressure, at the very entrance here where my lips are, there's a maximum amount of pressure. So this, if I'm drawing a curve for the air pressure, you can see the air pressure is at a maximum. Then here we have our first node, where the air pressure is at a minimum. Or sorry, it's not at a minimum, but it's sort of at a equilibrium point. Then it goes down to a minimum, and then back up to a node, the equilibrium, then up to a maximum, back to a node, like this. So this is what happens in our brass instruments and other things that have two free ends. You see that we have an antinode at the end here, and an antinode at the end here. And then it can have some number of nodes in between the two ends. And again, this one here that we've drawn, this has 1, 2, 3 nodes in between. So that has 3 nodes. And if I draw the minimum possible nodes that I can have here, well, if I know I need to, I'll do this in red. If I know I need to have an antinode at the top, so at one end it needs to have the largest possible value, and at the other end it also needs to have the largest possible value, or a minimum value, max or min. So it needs to go from an antinode to an antinode. The easiest way I can do that is like this, where I have an antinode at the top, one node in the middle, and an antinode at the bottom. And so we call that here, this is that's my fundamental frequency. So that's the first harmonic. Okay, and so that had one node. And if I draw one with 2 nodes, well, I could draw those 2 nodes, let's say here and here, and what's going to happen is I come down like this, back up, and like that. So you see now this has 2 nodes. It's an n of 2, which is our second harmonic. And then I drew the blue one already. We had 1, 2, 3 nodes, n equals 3, which is our third harmonic. And these harmonics, the way it works is just the first harmonic, it's the simplest possible standing wave I can make with the requirements that I have, that I have an antinode on both sides. The second harmonic is the next most complicated wave I can make. So as simple as it can be, but the next step. And then the third one, we're going up one more step, so we have one extra node. And that's how these harmonics work. Okay. So we're looking at now one last type of standing wave, which is where we have one fixed end and one free end. We call that fixed free. So fixed free is where we have one fixed end and one free end, and we have a node on the fixed end, and we have an antinode on the free end. Remember, node means it's at a minimum, or not at a minimum. Node means it doesn't move at all. And antinode means that it's moving the most, so it's at a maximum or a minimum there. Okay, and we see this fixed free situation, we see that the most in woodwind instruments. So like clarinets, saxophones, that sort of thing. And so we have a picture of that down below. Again, we've drawn an air column here. So we're talking about air pressure, not a string this time. So again, we have sort of our tube. This is our tube. And our tube is still open at the left end here, so you can see that it needs to have a maximum air pressure there. And on the right end, it's closed. And that's how, if you know about woodwind instruments, saxophones, that sort of thing, they have a reed on the end. And the reed creates this closed situation on the end where there is an equilibrium and it's not actually changing air pressure at all there. So again, if I want to connect my antinode to my node, well, that is not the simplest way to do it, because you see I've had two extra nodes in there. The simplest way, I can go from my antinode to my node with no extra nodes in there. You can see that it looks something like that. And it's basically half of a, or not half, it's basically a quarter of a sine wave there. And so that's going to be my n equals 1, which is my first harmonic. And I can draw the next one here with one extra node in between. And so that means I'm going to have sort of a 3/4 situation. Because I'm going to go down to my node and then back up like this. I'm going to have the same sort of thing over here like this. So you can see that I have almost a full period. If you're looking at a sine wave or something like that, you see I go from a node up, back to a node, down, and if I just continued it a bit further down here, we would have our full sine wave. So it's 3/4 of a sine wave. So this is our n equals 2, our second harmonic. And that had one extra node in there. And then you can see we have two extra nodes. Well, that's going to be our n equals 3, which is our third harmonic. So notice here it's a bit different between the, well, we'll go back to the fixed for a second. Notice the fixed, we had a node on either end, which means that we didn't need any extra nodes in between. We went from our node to an antinode down to a node again. So our fundamental had no extra nodes in between. Whereas for two free ends, free, the red guy needed to have one node in between, because it went from an antinode to an antinode. It needed to go through a node. It needed to go through that middle point once. And finally, for a fixed free, it didn't need to go through a middle point, didn't need to go through a node. So we have different situations here. Okay, now, if I have these situations, and I want to figure out the relationship between the length of our air column, or our string, and what wavelengths are on this, because remember, these all boil down to being wavelengths. You can see that for our string, here I have, goes up, down, and then back up again. It has one full wavelength on that string. Whereas if I look in my first one here, like this, that only has half a wavelength. And if I really wanted to complete that, I would need to continue it like this to get a full wavelength, to get, one full sine wave. Okay? And so that's what this equation down here is saying. It says L1 is equal to 1/2 of lambda. So if my wavelength here is twice as long as the string, then you can see that the string length is half of the wavelength. And now on the next one here, you can see L2, so the length for our second harmonic, is one full wavelength. And L3, you can see we've got 1, 2, So we've got 1.5 wavelengths there. So L3 is equal to 3/2 of a wavelength. And L4 is 2 wavelengths. It goes like this, and like that again, 2 full wavelengths. So this is our relationship here, and if we want to actually calculate those, we have some equations. And the equations are, for 2 fixed ends or 2 free ends, the equations actually come out the same. So this is to say that if I want the length for my nth harmonic, it is equal to n lambda over 2. So that's if I have, let's say I want my third harmonic, and I want to know how long my string needs to be for the third harmonic. Well, I take my wavelength, multiply it by 3, divide by 2, that gives me my length. And the other way we can do this is we can say if I have a fixed length of string, I can find what is the wavelength of my nth harmonic. And this is 2L over n. And you can see that these two equations are basically equivalent. I've just solved for L, or I've solved for lambda. So that's those two equations. And for fixed free, it's a slightly different situation because we remember we have this sort of quarter of a wavelength on the fundamental frequency. So what we get is this relationship. Ln is equal to 2n minus 1 lambda over 4. And again, we can write that this other way, solving for the wavelength. It's 4L over 2n minus 1. Good. Okay, so those are our equations. We've got 2 quick problems to try those out. It says the speed of a wave on a string with a fixed end and a free end is 350 meters per second. The frequency of the wave is 200 hertz. What length of the string is necessary to produce a standing wave with the first harmonic? So first harmonic, that tells us we're looking for n equals 1. And we have some other information here. Our frequency is 200 hertz. Our speed is 350 meters per second. And we know that v is equal to f lambda. So I can solve for lambda right now from that equation, v equals f lambda. So lambda is v over f. We get 350 over 200, which is 1.75 meters. And then I can say that the length for the nth harmonic is equal to, well, we're dealing with fixed free, so we need to use the second set of equations here. So we have 2n minus 1 times lambda over 4. So if I'm solving for the first harmonic, we get 2 times n, so 2 times 1 minus 1 times our lambda, which I can fill in that value. So 2 minus 1 times 1.75, all divided by 4. And this gives us 0.44 meters. So that's how long our string needs to be to get that first harmonic with that frequency. All right, and we have one last problem here. The sixth harmonic of a 65 centimeter string, guitar string, is heard. If the speed of sound on the string is that much, what is the frequency of the standing wave? So we have v is 206 meters per second. N is 6. We've got the sixth harmonic. And we know that the length is 0.65 meters. So since this is a guitar string, we're dealing with a fixed situation. That means we use this form of the equation. Ln is n lambda over 2. So we've got L6 is equal to 6 lambda over 2. We can fill in some numbers now. 0.65 is equal to 6 lambda over 2, which is 3 lambda. So that means that lambda is equal to 0.65 over 3, which is 0.2167 meters. That's our wavelength. And now we've got one last bit here. It asks what the frequency is. So we need to do V equals F lambda. Rearrange that to say that F is equal to V over lambda, and then plug in our numbers. 206 divided by 0.2167, which gives us 950 hertz. Okay, so I know that this lesson is a lot to take in. Take your time with it. Do try the homework problems, and try to get comfortable with the ideas. Please ask me if you don't understand what's going on. Great, good luck.